Hello everybody, welcome back to the channel. This is my first non-calculus video in a long time, and I have no idea why I never made this video in the past because it was the first kind of concept that I thought I would post on my YouTube channel way back in freshman year. I made a video before I even had a whiteboard of me deriving the quadratic formula on a piece of paper. Maybe I'll post that to my YouTube channel. If this gets, I'm going to be that YouTuber. If this gets 5 likes, I'll post that video of me deriving it in freshman year on my YouTube channel so you guys can see what I looked like in freshman year. And also, understand that I've been enjoying math for a long time, and I'm not just mixing things up. I have been enjoying math since freshman year. So if you guys want to see that, leave a like, and I'll post that. But this is going to be basically the same video, just deriving the quadratic formula on Jamboard instead. All right. So yet again, the purpose of today's video is to understand why the quadratic formula works, where it comes from, and how to derive it. All right. So I'll start by just writing the quadratic formula that we're probably all very familiar with. All right. The quadratic formula, what it does is it tells us the x-intercepts of a quadratic if we know its coefficients. So if we had a general quadratic that looks like this, right, it would tell us that the x-coordinates where the graph intersects the x-axis is given by this formula. That is x in terms of what the coefficients are. Because obviously the coefficients of the quadratic directly determine where the graph is going to intersect the x-axis. So that's why this equation is in terms of all of the coefficients. All right. But where does it come from and why does it work? Because in freshman year, most of us, we were kind of just given the formula and told it works and told to use it. So we're probably all very familiar with using it and plugging in our values to find x-intercepts. But I'm curious if we know actually why it works and where it comes from. And if we don't, that's what we're going to try and accomplish today. We're going to try and understand why it works and where it comes from. And I'm going to start doing that right now. So if we have our general quadratic, y equals ax squared plus bx plus c, all right, this graph or this function is going to intersect the x-axis, all right, and I'll just draw some random quadratic. That's terribly drawn. It's going to intersect the x-axis whenever its y-coordinate is 0, right, because you'll see that the x-coordinate exists at a height of y equals 0, so the x-intercepts are going to exist at a y-coordinate of 0, all right. So this can actually be really helpful if we're trying to figure out what the x-intercepts are of our quadratic, because if we know that the x-intercepts occur when y equals 0, then we can rewrite this equation as 0 equals ax squared plus bx plus c, because our x-intercepts exist when y equals 0. So we replace y with 0. All right. So now we only have one variable, right? Here we had y and x in 2 variables, right? But now we only have 1 variable and 3 constants. So we could solve for the variable in terms of the other constants, and that, with the logic I've outlined, would tell us the x-intercepts of, or not the x-intercepts, the x-coordinates of our x-intercepts, because they exist when y equals 0. So replacing y with 0 and then solving for x will give us the x-coordinates of our x-intercepts. Sorry, I keep mixing up the 2 terms because they're very similar. All right, so we understand the conceptuals now. We understand what we have to do. We have to solve this in terms of x. But how do we do that? It's not a simple linear equation. All right, most equations where we solve for x, we have x to the first power, or or just x squared. But very rarely do we have both an x squared and an x term. And what you'll probably notice is it's actually really hard to solve for x with our current with our middle school algebra techniques, right? When we only have one x and x to the first power, it's easy to solve for x with our middle school algebra techniques. But we need to use some of the concepts that we've been learning about quadratics to fully solve this equation for x. And one of those concepts is the idea of completing the square, which I will show when we get to that. So let's begin tackling this equation, all right? So the first thing I want to do with this equation is subtract c from both sides. So I'm going to get negative c equals ax squared plus bx. The original c here, we're subtracting c, so it goes away. And 0 here becomes negative c because we're subtracting c. Right. All right. Next, I'm going to divide both sides by a. So I'm going to get negative c over a equals x squared plus b over ax. All right. And now we're at a key point in our derivation process, because now we have to talk about what completing the square means. All right. So a rule that you probably learned in your factoring unit before taking quadratics is the fact that if you take c plus d, all right, and you square it, that's equal to c squared plus 2cd plus d squared. All right. So the idea is if we have something in this form, we could replace it with this, all right? And you'll notice we have a c squared term here, but if you bring it over here, our c becomes a linear term. It becomes just raised to the first power. And we want to get x to become a linear term or to become to the first power term because we know it's easier to solve for x if we're only dealing with x's to the first power, because then we can just use our middle school algebra to solve the question. All right. So if we can get this into a form that looks like this, we could rewrite it in this form and we'd be in business. All right. So let's try and see if we can find things up here that are analogous to things down here. All right. So you'll notice up here we have an x squared and down here we have a c squared. So these things are kind of analogous to each other. Additionally, in this term, we have something times x. And if we said x is analogous to c because the x squared looks like the c squared, then the something times x is analogous to the something times the d because, to the something times the c. So if up here we have something times x and up here we have something times c, and c and x are analogous to one each other, then the analogy for 2d in the above equation is b over a, all right, which is 2d. So if we want to find what up here is analogous to our d term, we just solve this simple algebraic equation. Our d is analogous to b over 2a, all right? So you'll see why this is vital in just a second. So if our d is analogous to b over 2a, what I'm going to do to the original equation, I'm going to rewrite it over here. All right, is I'm going to add b squared over 4a squared, all right, to both sides. And because we're doing it to both sides, it doesn't change the validity of the equation, because as long as we do the same thing to both sides, we're fine, all right? So let's look at what we have on the right, all right? What we have on the right is a perfect square. If the first term is x and the second term is b over 2a, all right, then x plus b over 2a squared, it'll give us x squared plus 2 times b over 2a times x plus b squared over 4a squared. That's the rule we said from earlier, right? Something plus something squared is the first thing squared, plus the last thing squared, this is the same thing as b over 2a squared, plus twice the first term times the second term. All right, so you'll see that what we have down here is the exact same thing as this. And what we have down here is the same thing as this, right? 2 times b over 2a is just b over 2a times x is b over a times x. So the thing we have below here is the exact same thing as what we have up here. So we could rewrite this thing as this, and that's exactly what we're going to do. So we have negative c over a, and we have to remember that we added b squared over 4a squared to this side as well, equals x plus b over a squared. All right, so we just factored the thing we had on the right-hand side of the equation before. We completed the square, and we know that our formula that we introduced before with the c's and d's, it shows that the thing we had on the right-hand side is equivalent to this, so the substitution is completely valid. All right. On the right-hand side, what I'm going to do is I'm going to try and combine these fractions by forming a common denominator. If I multiply the numerator by 4a and the denominator by 4a, all right, then the denominator becomes 4a squared. So we have a common denominator, and the numerator becomes 4ac. So I can combine these fractions like so. I can combine them because they have a common denominator. B squared minus 4ac over 4a squared equals x plus b over 2a. And some of you might be excited already because we noticed we have a b squared minus 4ac on the top. So we're starting to actually get close to the legitimate quadratic formula. It's starting to kind of poke its head out of the abyss here. So we're pretty close. All right, so the next thing we're going to do is we're going to take the square root of both sides, all right? So when we take the square root of this side, we're just left with x plus b over 2a, because something squared, you take the square root of it, you just get the original thing. If I took 3 and I squared it, and then I took the square root of that, I just get 3 again. If I take this term and I square it, and then take the square root of it, I just get this term again. So when we take the square root of both sides, we're going to get this term on its own. And on this side, we're going to get the square root, but we're going to have to put a plus or minus in front of it. And the reason we have to put a plus or minus in front of it is because you'll notice I could, let's say I'm trying to solve the equation x squared equals 4. All right. I could solve this by taking the square root of both sides and say, well, x is equal to 2. But the problem is there's a completely different solution that we ignore if we just do the method that we would think makes sense, but actually doesn't make sense. x equals -2 is also a perfectly valid solution to this equation, all right, because -2 times -2 is +4. But by taking the square root of both sides, we don't get that answer. So when we take the square root of both sides, we have to do plus or minus the square root, because you'll notice that plus or minus the square root of 4 gives us both answers. It gives us x equals 2 and x equals -2. So the plus or minus is analogous to this thing below. It just means that when we take the square root, there's two answers to the square root. There's the positive answer and the negative answer. So the answer is going to be plus or minus the square root of the thing we're taking. Similar to how when we took the square root of 4, if we solved x squared equals 4, the solution is plus or minus the square root of 4, plus or minus 2, which is 2, and minus 2. If you've never seen the plus or minus sign, by the way, it means when you see the plus or minus sign, it means there's two solutions, all right? So I could say that a solution is x equals plus or minus 2. I could write the two solutions as one thing, but this tells us that there's two solutions. This one equation encompasses the fact that x equals 2 is a solution and x equals -2. That's a terrible x. And x equals -2 is a solution. So when you see plus or minus, remember that the single equation is describing two solutions, because one of them uses the plus sign, the other one uses the minus sign. So similarly with the quadratic equation, remember we showed that quadratics often have two roots. Even though there's only one quadratic formula, there's a plus or minus. So the two answers will just differ by whether you use a plus sign or a minus sign, similarly to our answer to x squared equals 4. All right, so we get plus or minus the square root of b squared minus 4ac over 4a squared equals x plus, I think it was b over 2a. Yes. Okay, so one of our square root rules is if we take the square root of a over b, that's the same thing as the square root of a over the square root of b. And you'll notice the thing on the bottom is a perfect square. The square root of 4a squared is 2a. If I multiply 2a by itself, I get 4a squared. So it might be useful to use this rule because then the bottom will no longer be a square root and we'll just have a square root on the top. So that's what we're going to do. I'm going to simplify this square root fraction using the rule I just outlined. So we're going to get plus or minus the square root of b squared minus 4ac over 2a. And you can probably see the quadratic formula screaming at your head right now because we are very, very close. All right. So I just applied the rule that the square root of a over b equals the square root of a over the square root of b. So the plus or minus the square root of this equals plus or minus the square root of the top divided by the square root of the bottom thing, which is just 2a. So I just used this rule to simplify what we had on the right. All right. Awesome. I hope we're on the same page here. All right. So let me erase this last thing. Cool. All right, so we have this equals x plus b over 2a. To solve for x, all we have to do is subtract b over 2a from both sides. So when I do that, this will become 0, and we'll get a negative b over 2a over here. And you'll notice these two fractions have a common denominator here, so we can combine them. So the last thing we'll get is x equals negative b plus or minus the square root of b squared minus 4ac, all of it over 2a, because we combined fractions with a common denominator. And now we're done. So what we've done is we found a solution for the x-intercepts of a quadratic in terms of the coefficients, which is exactly what we set out to do. So that's where the quadratic formula comes from. I hope you enjoyed the video, and I'll see you guys another time.